Once again, welcome you to the lecture of linear induction motor. In this video, I will discuss about what is linear induction motor, type of linear induction motor, construction, its working principle, thrust force, application of linear induction motor, problem associated with linear induction motor. So take your pen and paper, be ready, stay tuned and get started. So what is linear induction motor? The basic design and construction of linear induction motor is similar to a three-phase induction motor, although it doesn't look like a conventional induction motor. If we cut the stator of a polyphase induction motor, lay on a flat surface is form the primary of the linear induction motor. Similarly, after cutting the rotor of an induction motor and making it flat, we get the secondary of the linear induction motor. According to the number of primary, it can be divided into two categories: single-sided linear induction motor and double-sided linear induction motor. In single-sided linear induction motor, there is one primary and one secondary. Therefore, we cannot utilize whole flux in single-sided linear induction motor. But in double-sided linear induction motor, it has primary on the either side of secondary for more efficient utilization of the flux from the both sides. Now we will discuss about the construction of a linear induction motor. The stator is cut axially and spread out flat in linear induction motor. In this type of motor, the stator and the rotor are called primary and secondary respectively. The secondary of a linear induction motor consists of a flat aluminum conductor with a ferromagnetic core. For understanding the construction of linear induction motor, we will first take a look at the construction of induction motor as shown in the figure. If we cut the stator along the limb AB and make it flat, the stator will be look like this. This is which makes the primary of a linear induction motor. So primary of a linear induction motor is flat and three-phase winding is wound on it. Now if we make the rotor of the induction motor flat, then it will be nothing but a sheet of flat aluminum steel, which is called secondary of linear induction motor as shown in the figure. Therefore, we can conclude that a linear induction motor has a primary totally consists of a magnetic core. It is generally laminated with coils into its slot. Now each phase giving an alternating polarity so that different phases are physically overlapped. Secondary is frequently a sheet of aluminium. Now I will discuss about the working principle of an induction motor. When the primary of a linear induction motor get excited by a balanced three-phase power supply, a flux start traveling along the entire length of the primary. This linearly traveling magnetic field is equivalent to the rotating magnetic field in the stator of three-phase induction motor. We know that when two pole pitch is crossed, one complete cycle of flux is generated. Assume that T is the linear pole pitch, that is pole to pole linear distance in meter. Therefore, 2T equal to distance travelled per unit cycle. If Fs is the supply frequency in Hertz, then Fs will be cycles per second. When we give supply to the system, the developed field will result in linear magnetic field. The velocity of the field is given by the equation Vs equal to 2t into Fs, that is distance travel per cycle into cycles per second. Therefore, that is equal to distance travel per unit cycle. Hence, it is to be noted that synchronous speed is not governed by the number of poles. Therefore, any linear speed can be achieved by achieving the pole pitch. The flux moves linearly, it induced current in the rotor plate. According to the Fleming left-hand rule, when a current carrying conductor is placed in an external magnetic field, the conductor experiences a force perpendicular to both the field and the direction of the current flow. Hold out your left hand with forefinger, second finger and thumb finger at right angle to one another. If the forefinger represents the direction of the field and second finger represents the current, thumb will be give the direction of the force. This is the basic linear induction motor working principle. The induced current interacts with the field, produces a thrust on the rotor plate and drags the rotor plate along the same direction. As S is the slip of the linear induction motor, therefore S equal to given by Ns minus Nr by Ns. But here, as it is linear speed, we will write here slip equal to Vs minus Vr by Vs. Now the speed of the secondary is less than the synchronous speed, that is given by 1 minus S into Vs. We know that force into velocity equal to power. Therefore, linear force will be given by air gap power divided by linear synchronous velocity. Now we will discuss about thrust force. The thrust velocity curve of a linear induction motor is similar to that of speed torque curve of rotary induction motor. If a rotary induction motor is compared with the linear induction motor, the linear induction motor requires larger air gap and hence the magnetizing current is greater and power factor and the efficiency of the motor is lower. In the rotary induction motor, the stator and the rotor area are same, whereas in linear induction motor, one of the two is shorter than the other. At steady state speed, the shorter path will passing continuously over a new part of the other member. Now we will discuss about the application of linear induction motor. The various applications of linear induction motor are as follows. The main application of linear induction motor is in transportation in electric traction system. The primary is mounted on the vehicles and secondary is laid on the track. It is used in the crane, pumping of liquid metals, actuators for the movement of doors, used in high voltage circuit breaker, also in accelerator. Now we will discuss about problem associated with linear induction motor. The linear induction motor is usually taken as an induction motor with three-phase balanced excitation, but this comparison is just an approximation. There are certain effects particularly to a linear induction motor which should be considered for accurate analysis. The two important effects are transverse edge effect and end effect. First we will discuss about transverse edge effect. There are two particularly effects occur in the linear induction motor but not in cylindrical induction motor. These effects are transverse edge effect and end effect. The path of the induced current in the secondary is not well defined because the secondary of the linear induction motor is a solid conducting path. The portion of the current path parallel to the direction of the motion of the secondary does not produce any useful thrust, but only contribute towards the loss. This is known as transverse edge effect in a linear induction motor. Because the current path parallel to the direction of the motion are more at the edge of the conducting plate. In linear induction motor with short primary, the current path towards the end of the field structure on the conducting plate go beyond the field structure. Such portion of current path do not produce any useful thrust but only contribute towards the motor loss. This is known as end effect of the linear induction motor. It can be efficiently reduced by increasing the number of poles on the motor.